Here's your warm up. It's recording, right? Okay, made a funny sound. All right, what's today's date? The 8th? All right, warm up. 5-8. You get your name. And it has you review a little bit of function stuff. So it says if two functions are inverses of each other, what must be true about their composition? Definitely a throwback. So what would happen if I compose these two together? Or maybe the other way around. We talked a little bit about this back when we were learning inverse functions. So two functions are inverses of each other. What's true about their composition? YouTube chicken, usual. Berman chicken here. Logan. You guys usually check in. You guys here bundle up. Okay. Chicken killer, you guys check in. You guys check in with each other. Maybe I'll have a YouTube chicken. Okay. Check in. Maybe above. No, check in. Yeah. You're four here to check in. Just in time. So if you guys look back in your notes from section, what was it? Inverse functions, section 3.6, week 3. Yep, it's a throwback. You guys can remember anything about their composition. It's okay if you don't. But I know some of you do from what I saw on your sheet. Residence getting cold. This is important. Okay, guys, do a quick check-in with the groups that I placed you with. Just do a quick check-in. I do see some of you guys writing stuff.
The first one is like F of the negative. And the first one is like inverse. Like right now.
Yeah, I think I really.
Yeah, I just said.
Like what you were talking about today?
No, that's really changed.
No, I meant like the function. It's like.
What? There was a relationship between F and its inverse when you compose them.
And then. What that is.
Yes. Yeah, if you plug in,
That's the.
if you plug in the inverse function,
Yeah,
All right, I'm gonna give you guys a hint. Okay. Remember when we were doing this, we said, let's say here's an X value, and we're gonna plug that X value into F. Then that gave you a Y value, right? And that's what happens when you plugged it into F. But then that Y value is gonna get plugged in where? Here's the other hint. Remember, this means this. Composition notation, right?
Yeah.
And this one means this. So X gets plugged into F. Gives you some number, and then that number gets plugged into F inverse, but it's a special property of what happens with that. That's my hint. That's my hint. See if you can use whatever that hint looks like to you. To conclude what would happen.
Yeah.
Maybe that was something.
So it's that, the thing.
Any ideas? They're both 1-to-1. You got that? That's for sure true.
Are there domain and ranges that we flipped?
Yeah.
The domains and ranges get flipped, correct? But there was something really nice that this will always equal. What is it? It'll always equal X. Okay? Basically, whatever the function looks like for F or F inverse, whatever it is, when they get composed with one another, they all reduce always to X. And that's because whatever I plug into F, whatever that looks like, when I plug it to inverse, it undoes all the operations and gives you back X. Okay? Yeah.
Is this the problem where we always have to switch the X into Y before solving it?
That's when you're trying to find F inverse, correct? Yeah. So like, let me give you a simple example. Let's say F of X was the square root of 1 plus X. The inverse is going to be, let's see, going to be X squared plus minus 1. Okay. Plug in 3 here. Plug in a 3. What do we get? Square root of 4, which is 2. So then if, like Alexa was saying, if we flip the domain and ranges, then when I plug in -2 here, or sorry, 2 here. Uh-oh, hope that works. What is it? What is that? It's 3. All right, good. So yes, these are the inverse functions of each other. But notice what happens if you compose. Let's say we plug this guy into this function. Right? Then this square root of X plus 1 gets plugged in here.
And that's also right?
Yep,
And minus 1 at the end.
like that, right?
Yeah.
Is that cool? What happens with the square and the square root? It cancels, so this just becomes X plus 1 minus 1, which is X. And that's kind of what this property was saying. If we were to do it the other way around, same thing would happen. Okay? That's a property of inverse functions, that when you compose them with one another, boom, they always will cancel the X. No matter the direction. Nice little property. Cool? All right, we're gonna use that because we learned last week that exponential functions and log functions are inverses of one. All right, so we'll see how that shows up. Pass up your warm-ups. Forcing you guys to review, just a little bit. Pass it up. I think next class I might bring back some candy. You guys pass up some candy. Yes, you're still very low energy. I don't blame you. It's that time of the semester.
Recent?
You want, oh, okay.
Not nice.
Okay. Recess. I'll see what's that. But that has peanut butter, right?
Yes.
Oh, anybody allergic to peanuts? Allergic? Maybe I'll bring up two options, non-peanut and then peanut. We'll see. Okay, let's see. So we're gonna use this fact right here to start off today's to continue the log properties here. So let's continue. We were on section 5.4. Log properties. And then this is part 2. So last class on Wednesday, what we found was that if f of x, f of x equaling some base to the x, and if we try to solve the inverse function of that, what was it? What did it look like? If you guys look up your notes from Wednesday. If this function was 5 to the x, the inverse would be
Wait, no, would it be X? No.
so this one's an exponential function.
Oh,
Why?
log base.
Oh, yeah, log.
Yeah, this one's an exponential function. So what we saw last class is that the inverse will have to be a log. But it's log base,
B.
whatever that b is. Perfect. Of x.
Would that be the natural?
Natural is if the base was the rational number e. Yeah. And so this one is a logarithmic function. And so these are inverses of each other. And because they're inverses of each other, they have to respect this rule, because this is true no matter the types of functions that you're doing. Okay. And so therefore, what we have is that if I do f and I compose it with its inverse function, it has to equal x, and the other way around is true as well. I plug in f into f inverse, that's going to have to give you x. And I just didn't want to say this because that's a big thing that happened that I wanted you guys to remember. Okay, but here, let's do this carefully. We know this has to happen. This composition has to equal x. Okay. So what does that mean? That means that the log function is being plugged in where?
Into the
Into the
X.
Into this little x. And that's gonna look really weird, okay? So that means that b to the power of the inverse function, this is going to have to equal x. And so in your calculator, if you were to do like 10 to the common log of any number, it'll just give you the same number. But it's very strange looking. And then the other one is doing the opposite. It's saying that in the log function, you're going to plug in b of x. So see, you guys see where this x is right here? We're going to replace it with f. So this becomes the b of x here. So it's going to look like this. Log base b of x is going to have to equal x.
I feel like the log one makes a little more sense visually.
It makes a little more sense because remember we said last class that the log has to equal the exponent, right? So how would you how would I write this in exponential form? Remember I had you guys turn logs
Yeah.
forms to exponential forms?
Date or
Would it be
p of
b
x
of
and
x
p of x,
equals
or p
b?
p to x power, yeah.
Yeah. Which is true, right? B to the x does equal b to the x. So that's why you're seeing kind of why this is happening here, okay? But algebraically, the way you're going to use this is what this one is saying is you can cancel algebraically. Okay, what's happening is that if I have some base and I raise it to the log base b of that same base, it's kind of the way that the square and the square root canceled. The log base b and it being an exponent of b cancel to just end up giving you x. Kind of what's happening. But let me write that in words. So you can cancel a log by having it be raised to its own base. That's going to show up later on with some of the algebra. And what this one is saying is you can cancel a base by taking the log of it with the same base. Sounds a little repetitive, but it's the same base. But they're actually kind of saying two different things. And we'll see this show up in later on. Okay? And so last class we learned 4 of the definitions of logs, and then I showed you guys how to do it with calculators, right? But sometimes it can be kind of complex doing it on a calculator, especially if there's like square roots and all this weird stuff that you have to do with calculators. So you want to use some of these shortcuts to help you compute your logs or your expressions. So let me show you. So let's say I asked you, what's the L natural log of the square root of e? You could do that on your calculator. You could take the square root of e and then press the LN button and it'll give you an answer. Yeah.
Is there also possibility it's on square roots of the
Is it possible to cancel square? Kind of. I'm going to show you in a little bit with another rule we'll learn how you'll do that. Basically, you're going to rewrite them as exponent.
Yeah, take the 1/2, right?
Exactly, yeah. And that's kind of what we're going to do here. See how you guys see how this is inside of a log? So if I can write what's inside as a power, I might be able to use this rule. So if I write this ln of how can I rewrite this as a power? E to the 1/2. But ln really means log base e, right? So what I really have here is I really have that. So I'm taking the log base e of something with the same base to that power. So then this property says the logs and the base, like the log and the exponent part cancel, and you just end up with an x. So yes, it'll just equal 1. Okay. Now let's say I did something like this. Let's use a log that's not natural or common log. Log base 2 of 8. Is there a way to write, if you can figure out a way to write this number as an exponential form with the same base 2, then we can use this again. Yeah, you can say, oh, look, 8 is just 2 to the third power. So this base and this base are the same. So they cancel. And I just end up with a 3.
It's the difference in with that, and like if you already know that 2 to the power of 3, like why wouldn't you just make the answer 3 then?
Yeah, no, so this is a very simple example to show you that this rule works, because there's gonna be more complicated examples where it might not be like that. Like, let me give you one, Eric. Now that you asked first. Okay. Let's say it's like this. Log base of base 2 of 1 over 64. Okay. Can we write 1 over 64 as a power of 2? That's the goal. Okay. Can you write 64 as a power of 2? What is 2 to what power is 64? Close. Let's see, it's 2, 4,
6.
it's 6. Okay, 6. So this is really log base 2 of 1 over 2 to the 6. But how, I don't want the base on the bottom, right? I don't have a fraction. I want the 2 up. So make it so that it's a negative exponent. So it's 2 to the power of -6. And now I have a base and the same base here. So if I use this rule, what is that supposed to equal? -6. Yeah, the log base 2 and the power of 2 cancel to just give me a -6. Perfect. So that's a more complicated. Sometimes there's square roots and all that stuff. Yeah. Questions? Yeah. We did that just to get -6. Yeah. So what we're gonna do is we did 2 properties right now. We got, these are called the inverse properties. Okay. And so let's name them here. These are the inverse.
So the B's have to match in order to find that.
The B's have to match. That's 100% true. Yes. These are the log properties, inverse log properties. Now we're gonna learn 3 more properties. And then what we're gonna do is we're gonna play with them. So right now we solved this way. We're gonna see that we can solve it a different way later on. Okay. But yeah, if you put that in your calculator, boom. 2 to the power of -6 will equal 1 over 64. That's kind of what that will show you right there. All right. We're going to use these ones to conclude kind of a little bit more of special cases. So consider the following, where again we want B to be some positive number. What have we been saying? A positive number raised to 0 will always be 1. Always be 1, right? What about that same positive number raised to the power of 1?
Itself.
It's itself, right? So if I plug those special cases into the second property right here, notice what this is telling us is that the log base B of 1 is really e to the 0. So if I try to use this property with this fact, what is log base B of 1 then always be? It's gonna always be 0. And this is true for any single base, no matter what base you have. And then if I do log base B of itself, that's really base B to what power? 1. So what should this always equal? 1. And so these two are kind of special cases of this guy. But this one is very, very used a lot in this section. Any log of 1 is always 0. Okay? And any log base b of itself is just going to be, they cancel to 1. And we'll see that being used later.
Why not the exponents of zeros or one?
Why is it that like this particular scenario? Let me give you a fast explanation, okay? Let's see, so we got B, so the question is, why is this true? Right, I don't think we really want that. Let me see, how can I do this? Okay, I got a B, right? And I'm gonna multiply it by another B. So that's gonna give me what? If I multiply it by another B, I get another B, right? If I multiply this by another B. Maybe, never continue that. Like that, cool? Now let me go backwards though. How can I go from this one to this one? I have to divide by B. So I would have to divide this by B. And that gives me B cubed, right? And I got to go backwards here, I have to do the same thing. Divide by B. To go here, I have to divide by B. But now to go here, B to the power of 1 is just B, right? But if I want to continue this pattern, and I divide this by B, that's the 1. But if I want to continue this pattern of powers, I would need this guy to be B to the 0. Right? And then let's see, what happens if I keep going? 1 divided by B is going to be 1 over B. But if I continue the pattern of these exponents, that should be 1 over B, which is matching. And so there's kind of like this agreed convention that we're going to have B to the positive number raised to the 0th power will be equal to 1, because it's really just going to divide by itself. And that's why you don't want B to be 0, because then this pattern you can't do that with these. Yeah. So we need this to happen, because this should be true for any base B. Kind of my fast explanation. Okay. Cool. Yeah. Okay, so let me see. So we got this bad boy. These are special cases that we're going to use. Because this is always true, this will always be true. Okay. All right. Ooh. And so I'll leave this here. All right, let me have you guys try just a few. Without a calculator, I want you guys to do the following ones. 2, 3, 4. All right, so try these out on your own. Log of 10. Log base 5 of 1 over 5. ln of e and ln of 1. Just a quick little concept check there. No calculator. Do it all with your supercomputer in your head. So you gotta find what it equals, okay? You're not converting it to like exponential form. Let's see what it equals. Take a quick check with your classmates, make sure you guys agree with that. See if they got the same thing. I did see some different answers.
Oh. One. I got one. One negative. I negative. Second. What was the one? One negative, one there. Right. Yeah. And that was negative. Not four. There you go.
Oh, I got it.
Yeah. I think it was like. Oh, it's like the third one.
All right, let me write the one that we were using here. Let's see, so this is supposed to equal X, and then we have these three here. So what base is this log? Really base 10, right? So then this should be log base B of itself with B is just 1, and it's true. 10 to the power of 1 is 10. Here, what did you have to do for this guy? Yeah, you have to write this as log base 5, 5 to the negative 1, so then it equaled negative 1. So negative 1. This is really log base E. Log base B of itself is a 1. And then the log of any base of 1 is going to be 0. Okay? And so these little guys will show up throughout the class. And so this is how you're going to be using these inverse logs here, inverse log properties. Any questions on these ones? Okay, so now we're gonna do the last three properties, and then that's where it's gonna get kind of fun, meaning spicy. Okay. These are called expanding and condensing logs with these three properties we're gonna use. And so from the exponential properties that I covered with you guys last class or last week, so from properties of exponents, we did last week, I believe we looked at these two properties, right? We looked at that one. B to the power of n times b to the power of m is b to the power of n, and then you add them, right? Good. And then we have b to the power of n divided by b to the power of m. When you have division, it was b to the power of the top minus the bottom. Next point. And then I think we had one more, which was that one. I have b raised to some power, but then I raise all that to a different power of m. What happens to the exponents? It becomes a product. That's right, 8 times. There was more. But these three translates to the log world. Okay. We're gonna start with this one. On the left-hand side of this equation, what mathematical operation do you see happening? Multiplication, addition, subtraction, or division? On the left, multiplication. So over here, we got multiplication. And then on the right, we have addition. Right? Let's look at this point. On the left, we have division. And on the right, we have subtraction. This one's a little weird. But what operation is happening here? Exponential. So you have exponential because there's not multiplication. I guess technically there's multiplication, but it's exponential, and then here it's multiplication. Okay.
So basically the one to the right is like the kind of dumbed down.
Sure. Yeah, because it's simpler. Like basically, instead of having multiple bases, or it's all clumped up together in one. Yeah.
Technically, you can add yourself to multiplication, so yes, and yeah.
Yeah, I see what you mean. Cool. So these properties are gonna also translate into the log world. And they have their own names. And so from this this exponential property that combines multiplication with addition, we have a product law, or product rule for logs. It looks a little different though, okay? So it's saying, if I take the log base b, and I have two things inside of, multiplying, it turns out that I take the log base b of the first thing that's multiplying. I take a different log base b of the second thing that's multiplying. And remember that logs equal exponents? So this is technically an exponent of something, and this is an exponent of something else. And so because the exponents end up adding, the logs end up adding. Okay, so this first property will produce this product of logs. On the left, I have multiplication. On the right, I have addition, just the way we had it this time. This second exponent property produces another rule called the quotient rule. That says if I take the log base b and I have something inside of it dividing, you guys see how here we subtracted the top exponent minus the bottom exponent? So here, what's going to happen is I take the log base b of the top. I take the log base b of the bottom. And I'm going to do the top minus the bottom. We get a minus, that's subtraction. And this stems from this exponential property. And then the last one is called the power rule. It says if I take the log base b of, let me see if I can match it with that, of n to the power of m. This one's weird, okay? I'll explain this part. I have the log base b of n, right? Which is representing an exponent. But that exponent gets multiplied with m. So it's through that relationship, okay, what's going to happen is that this m that was an exponent, the way this m was an exponent, but for logs, it ends up dropping down in front of your log so that it multiplies with log base b of f.
So
This one's weird.
thousand was gonna be log b n times.
Yeah. Mhm. And so something we've done a lot in this class is like kind of used identities. Where I either have the left and then I rewrite it with the right. Or I have the right and I rewrite it with the left side, right? You've kind of been doing that with identities. So if you replace what's on the left with and rewrite it so that it matches with what's on the right, that's when you're what's called expanding. You're expanding. You're going from something that has one log to something that has multiple logs. But if you go the other way, that's called condensing. Something that has multiple logs, I'm condensing it so that I write it with only one log instead. And so on the homework, and then in the future, when you guys get to calculus, you're going to use these rules a lot. And so let's first play with expanding. So let's say we're asked to expand. And let's see how this is going to look like. So we did this, you guys did this right here. Look. Let me write it better.
Oh, thank you, sorry.
Sorry. Example, and then the instructions are to expand. Let's do log base 5 of 1/5. You guys already did that. Right here, but now we're gonna do it a completely different way. Okay. Inside of the log, what operation do you have? You have division, so that's gonna be quotient. That says if I take the log base b of a fraction or of a division inside of it, I do the log base b of the top minus the log base b of the bottom. So log base, and these bases have to be exactly the same bases.
So the basis
5 of the top minus log base 5 of the bottom. Right? But now from here, use these guys.
So then, yeah.
What's the log base of 1, no matter the base, is always going to be 0. And the log base 5 of itself is minus the 1. So 0 minus 1? -1. Same answer you guys got earlier. Okay?
Are they only useful in circumstances where those results would appear?
They're useful, definitely useful when these results appear. And what we're going to see is that, yes, I'll just say that. Yes. I'll keep it there. So I'm going to get a little spicier with each. I'm going to get really spicy with the third example. Okay. Remember, I'm going off of spicy with the wings. That's what I mean by spicy. Not like other kind of spicy, but log. I'll let you interpret whatever that meant. Okay, so here, what's going to be tricky is when there's a whole bunch of operations inside, and you want to make sure you do this carefully. Okay. Don't rush it, especially if it's something that maybe it's your first time seeing, or you kind of struggled with it in the past. Okay. I have an exponent and I have a product inside, right? But this exponent rule, this power rule, will only work if the entire thing is being raised to that power of m. If only some of them are being raised to the power of m, I can't use this power rule. So instead, I'm going to use this one first to split it up. These two things. So I have, this is like my x squared and this is like my y. So it's going to be log of the first product or the first factor here. And then what I write here? Plus log of y. You know you're done expanding when you can't use any rules anymore. If you can still use these rules, then you're not expanding. You gotta keep going. Okay? Can we do anything with log of y? No. What about this guy? See, now I have everything inside being squared, right? So now that rule is which rule again? Power rule. So then this becomes 2 x plus log 1.
And if there's no base, it's 10.
And if there's no base, it's 10. Exactly. All right, let's do the third one. So, yeah, so you would say, can I do product, quotient, or power rule to this? No, no, I'm done. That's how you know you're done.
Can you solve for?
No, because you're not being asked to solve for x and y. Yeah, all you're being asked to do is expand. Yeah. Here, there was more we can do because these weren't variables, they were numbers. So I was actually able to compute these in this case. Okay. If in the previous answer, let me change it. Let's say this would have been like a 3. And this would have been a 3. Here, I couldn't use any of those inverse properties. Here I could have. So the way you would leave this answer is log base 5 of 3. That one, what did it equal? -1. So then the answer would look like this.
What it want us to do that. Well, 10 over log of y and calculate and find out.
Oh. If it asked you to round it to the decimal value, then you would use a calculator to compute all of it. Correct. Correct. But if it says expand, it'll, and you can't like simplify it the way we did earlier, because this is not the same base, then you're going to leave it in log form. All right, let's try this third one, and then I'm going to have you guys try one out. All right, log of the 4th root of x minus 3 squared over x times x plus 3. A big old one, right? And we have like a root there. So this is technically inside this big old parenthesis like this. For these guys, whenever you have roots, convert them to power, because then this guy will show up. Okay. So how can we write the 4th root as a power? 1/4, right? So I can write this as the log of this whole thing inside, x minus 3 squared, x times x plus 3, and all of this is being raised to the 1/4, like that. Not negative, because the negatives have to do with reciprocals. The 4th root just gets converted to a power of 1/4. All right, look, the difference between this problem and this problem is that here the square was only affecting the x, versus here the power is raising all of this to that power. So in this case, I could use the power rule first, because all of that is being raised to that m.
Which do you choose?
M will be whatever that exponent is.
Is it 1/4 or is it -4?
It's 1/4. So
You can't put -4.
no. So here, let me remind you guys. 1 over x to the 4th versus the 4th root of x. This is when it's a negative, x to the -4. When you write it as a reciprocal. A root is when you write it as the power of 1 over that root. Like that. Yeah, so just be careful. I think that was similar. Yes, so it's this one. Okay, so if I try to use the power rule here, this whole thing right here, this big old thing is like the n. And the 1/4 is like the n. So what happens to that 1/4? There's one
Oh,
fourth,
oh, no, yeah, 1/4 goes to the front.
it drops to the front right there and multiplies with that log. Like that. And then I'm left with whatever is inside. Like that. But now that power is gone. Whew. We still got hella crap in there, right?
Well, and then we still have the power.
And we still have the power of two, but is that two raising all of that? No, it's just the top, right? And this is a product, but is this multiplying with that? No, so what do you think would be the next one? Quotient. Let's separate these into their individual ones. So it's gonna be one, here's where you gotta be careful though. This is why I wanted to show this example. Correct. This 1/4, let me just do this step by step. This 1/4 is multiplying that, right? So technically this, I'm gonna skip this part. Technically this is gonna be log of something here minus log of something here. Right? But that is this part, and this part is being multiplied to 1/4. So that 1/4 needs to get distributed in there. Okay? The textbook won't do that though. They're just gonna write it like this. They're gonna write it as 1/4 log of the top minus 1/4. That's where you might get frustrated with your answer being wrong, if you forget that 1/4. So be careful. Like that. Eric, yeah. Yeah, so from here, that 1/4, remember that 1/4 right there, that 1/4 is multiplying this guy right here, right? This, if I use the power rule, where does this 2 drop? To the front. So what's happening is that you have this. So that 2 multiplies with the 1/4. Because all of these 3 things are multiplied.
But we don't have to solve any further.
Well, let's see, hold on. So this one, there was still another rule to use, right? It was a power rule. So I bring it down, but then Eric's question was, what do I do with that 2? Do I multiply it to the 4 or on top? And the answer is, this 2 is just 2/1. So multiply to the top. So it'd be 2/4, which is 1/2, correct? And multiplies with the log of x minus 3. Here, this 1/4 is multiplying this whole log. What can I do here? You can distribute, but if you distribute, you're undoing the fact that it's a product.
Because then you get an X squared.
So then because if I distribute it, then it's gonna give me this. And I can't write this as product of 2 things. Now it's just a sum. And so none of these rules use sum inside of the log. No.
Why is squaring it turn it into 1/2 rather than 1/16?
Doesn't, when I brought down the 2? What was your question again?
If it's squaring, wouldn't it turn into 1/16?
Well, this, right now, this is being squared.
Okay.
But the power rule doesn't square the whole thing. What ends up happening is that you turn from exponential to multiplication. So the m multiplies with the
Okay.
log. Yeah, and so that's why that 2 multiplies with the 1/4. Not, it doesn't raise it to the power. Here, what rule do we use for these 2 things? Yeah, the x is like the m, and the x plus 3 will be like the m. Because they're multiplying. But be careful, that minus 1/4 that's in front is gonna end up multiplying when I do this product here. Right? So that 1/4 will end up distributing. So it's gonna become the negative, say it again?
With the negative 1/4?
with the negative come with it, because it's negative. So this is gonna become negative 1/4 of log of X. Plus, right, but because that negative 1/4 follows it, minus 1/4 log of
Yes.
X plus 3. So then I look inside this log, is there a product, a division, or a power? No. No, and no. Even if this had a power, that wouldn't work because that is not the whole thing. Yeah. And I can't separate it because it's a plus, not a product. So that's where it's gonna get tricky. Okay? I don't wanna move any of the stuff I did here. So let me give you guys your practice one here. All right, so expand this sucker. And be careful. Be careful with the steps. Log of 3a over the square root of b times c.
You're gonna do condense ones too.
Yeah, after this practice. And after, we'll do this and then a break, and then we'll do the condensing stuff. Oh. No, because if you let like people laws of that. You can write the other one. So they all have to be the same. They all. Yeah, the other one have to be. Like the whole law would have to be spread. Well, we eventually use. I don't think so. Unless it's like really insane. Most of them. Try this one with your group. A little spicy on that one.
Oh, sorry.
Ooh, you almost.
This is
like
I saved it.
the break.
Thank you.
All right, guys, just check your work real fast with your groups. See if you guys are in the same track. Some of you guys seem to be a little stuck.
Where are you going?
You don't really know that.
That's not.
So like,
Yeah.
Yeah, it makes-
Yeah.
Yeah, you do a fraction.
Oh, square.
So, you know, so
Well,
that's the one, so you change that. Square root of BC.
at this point, you have.
I mean, it's-
Yeah, but I'm still right away.
Yeah, but you're adding a negative. It's the negative one half, that. It was minus one half.
Like, you know, over here, there is square root one. Now, you know what word is square. You don't have to make it. It's not. But because I split them up first. Yeah.
Yeah, I was talking
Help to understand that. I think we're gonna do something, but not at all.
Is BC in this?
Exactly.
It's in this.
Yeah.
I don't think you. Use the product rules. Because it's.
Yeah,
It's
yeah.
Yeah.
Yeah, it's the one out there, it's 26.
Yeah.
Yeah, yeah.
I feel like that high one, I'm like, I can do it, I can do it. I can do it.
Yeah.
Just.
I forget this when I was.
You can check your work up there, I'll keep going around.
Yeah. Make sure you know your dimensional model really well.
It's gonna be good.
No, no, the way. And they probably mentioned. Exemption.
So good.
All right, guys, looking good. So what's the first rule that you would use to separate these two? Quotient rule, and you separate that into a 3a. The square root of BC is really BC to the power of 1/2. Then the 1/2 would drop. Right?
Yeah.
The 1/2 would drop. So you end up with log of BC. Product rule here, product rule here. But because you use the product rule here, just be careful that that negative 1/2 distributes. Okay? All right, so this is expanding. Let's take a break and then we'll go backwards. Condense. So come back at 2:09. 2:09. So resume at 2:09.
Oh, I guess it's.
Thank you. All right, bring it back. Okay, can you guys read that back there? It's a little small, sorry. Can you read it? This is the product rule, quotient rule, power rule. It's a little small, sorry. But they should be on your notes as well. We're gonna reference them again right now. Okay, guys, so. Like I said, we were just expanding, going from left to right, right? And now we're gonna go backwards. So let me show you guys what that's gonna look like. And this is called condensing. Let's condense. And actually, let me do it. Let me do it here so I have more room. The thing about condensing is that there can be multiple ways of doing it. And that's where it's like, oh no, did I do it right? Did I do it wrong? It's just maybe there's different ways of doing it. So let's say we're gonna condense 3 log base 2 of x plus log base 2 of y minus log base 2 of z.
Are you allowed to start it anywhere you want?
That's that's where it's like, sometimes you can start wherever you want, yes. And then other times it's like, oh, I have to start at this step. Okay. You won't get it wrong if you go from left to right. As long as you use the properties correct. Okay. So I'm gonna do that. I'm gonna go from left to right. And then chat a little bit what happens if I get it in a different way. Okay, we go from left to right. Do you guys see the power rule? How there, if there's a number in front of the log, and I try to use the power rule, that number in front of the log goes
Above that.
above. It raises whatever the log, what I'm taking the log of, and I raise it to that power of n. So there's this 3 in front of this log. So that 3 is going to now become x cubed. Correct. So this becomes log base 2, and then I undo the power rule so that it raises that x to a power of 3. Okay. And then here at this point is your style, okay? Some students like to do only one rule at a time. So I want to do all the power rules, power rules, and then all the product rules and so on. So how do I do a power rule here? There's no number in front, and then there's kind of a number in front, but you want to do quotient rule instead? Okay. So then we would see that minus right there. So if I use the quotient rule, be careful, it's not log base 2 of y divided by log base 2 of z. It's gonna be tempting, okay? But if I'm subtracting outside, I divide inside. So then this right here uses a quotient rule, and it becomes log base 2 of
Y over Z.
inside the log y over z, exactly. And then now I have a plus of 2 logs. So if I add 2 logs, I multiply inside. Well, let's see what that looks like. Log base 2 of
X cubed times y over z.
over z, correct.
Oh, dang, I got it wrong. I put all the way over z.
It's true. Yeah, because this is really over 1.
Okay.
So then you multiply the numerators, denominators. And this becomes log base 2 of x squared times the y, 1 times z, so it goes like that. Okay. You could have done this a different way. Let me show you guys another way that you could have done it. I did the power rule, right? I brought that 3 up there. Let me just write what I had earlier. What you could have also done is you could have done the product rule here. What happens if these 2 are adding, right? We'll leave this one off on its own. So if I add these 2, add outside, then I multiply x cubed times y. And then I use the quotient rule, top over bottom. And it gives you the same answer. Okay. So if you find, that WebAssign is doing it one way versus you're doing it a different way, they might both be right. Cool. Okay. What would happen? What would change if we had this instead? Like that.
The three would be squaring everything outside the parentheses on the side.
The three, you're gonna wanna do what?
Oh, it would square the X and the Y.
Yeah,
Y.
you distribute that three in there first. And then because you distributed that three here. It's gonna raise both of those to the third power. And then you will continue from there.
But if you put the X and Y, yeah.
Yeah, that's what I'm
yeah.
You could have also done that.
And then just done with it.
Yep, when you, no matter what, when you put these together, it would have became log of,
X, Y.
you could write it x cubed, y cubed, or you could have written it as x, y cubed.
Either one would be fine.
Either one would be correct, yeah. And then because this is minus.
It would be the character we put outside, because I think that's easy.
Okay, so what I have for you guys is a sheet with all the rules that we just covered, so that you have them for the homework. And then a couple practice problems. You might not finish the back ones, but if you do, that's okay. All right, let me have you guys play around with these real quick. Here we go. Zero. All right, so we'll start with condensing. And then some problems and then expanding, because expanding is a little bit harder. You have. You wanna take this one? Look this one, okay? Okay, who doesn't sell it? Coming, right? 1, 2. Oh, my M's and N's are swapped, but the rule's still the same. Sorry, you really suck. Loose. The solutions to this worksheet have been posted, okay? No, week 16 module. Forgot to say one thing, guys. For condensing, you know you're finished when you only have one log. If you have more than one log left, you're not finished. At the end of your condensing, everything should just be with one log.
Made it multiple ways and we could have one line and.
Yeah, it might be written in different ways, like x cubed, y cubed. But assuming everything was right,
Wait, I have a question. For the second one, do we have to put it in log form, or is it okay if the last thing is in LN? As long as you want LN, or do you want us to switch the LN from to log? And then this is nice.
Ellen is just a fancy log, basically. So yes, just Ellen is fine. And then don't forget these exponent properties, don't confuse them. One's an nth root, one's a reciprocal. Forget these guys.
Be careful. Sometimes there's multiple minuses. I got you for that. Yeah. And then why it's. So it has to be the whole thing. So you have. It's still. If you don't. Okay. Yeah. This one thing. Yeah. Thanks. Break it down. You see, but then I don't know how to change. So when you do convulsing, that's what you do. The convulsing, and then make this a this was as a power. One third is also correct. And has a certain difference. Basically, this extent. So like, so here we go. Yeah, yeah, yeah.
That's the one. Wait, would it be 24x? No.
Well, yeah, so is that for? Is that for raising 6 ounces of the power flow? I'm so lower down.
Four is gonna, it's like the first one, design, four. Or so six is not gonna be known, that's not because the way that it's. Kind of like, no, I know it.
It's kind of like this, exactly.
So
Class, just a quick thing. A quick thing. We've been doing we've been doing the product rule when there's two things multiplying, right? But if there are multiple things multiplying, like let's say I got the log of a time or ABC squared. I got 3 things multiplying now.
So it's like one A times one, B times one, B squared.
These things are multiplying. So if I want to use this property, let me show you what happens. You basically have to pair one of these 2 things. So I can think of, let's say this times c squared. You guys see that?
Yeah.
So it's like the AB times the c. So I can think of the AB as like the n and the c squared as like the m. So then if I use the product rule, it'll be log of the n, which is the AB part, plus the log of the m, which is the c squared part. Let me get rid of the square.
I see what you're saying, because after that, the A, B would then be added.
Then you do the log, exactly. Then you use the product rule on this guy. So then that becomes the log of A plus the log of B plus the log of C.
Can you put the square up in there? And then from there, we log A plus log B plus log C plus log C.
Not plus, sure, but instead you're gonna want to use the power rule.
Log A plus log B plus 2
Log C, exactly, yeah. Yeah, so but basically my point is if you have 3 things multiplying, then they all split up as additions. So just be careful. I think that's for number 2. That kind of applies, yeah, Eric, what's up? Yeah. See. This could be good considerations. Reset it. Okay. This would be number 5. Number that is. And then there's a rest for the here, right? Yeah. And then. Yeah. So think of it like this one. Then stop. Okay, basically, you have to do shit. So you see how right here we have negative 1.12 and DC. So when I use the product rule to split up, that negative 1.5 distributes to both of them. So then it's exactly. You distribute it good. And then factor do something like, yeah, so there's no other copies to use. I think I was system recording. Yeah. If you start here, you're going to want to. So if you look at the notes, the condensing means you're going to use these rules that go in. So like for example, this 3. But this 3. If I go that way, that 3 moves up. Goes up here. And this case, this 3 would move up and go and they what to the higher level. So when you're doing this rule, for example, convention for each side, ignore everything else and just focus on that. Exactly. And so there's 1/3. Think of that 1/3 as the end.
And then you're gonna use the power rule for this one and this one separately.
Oh, okay. Oh, okay.
Exactly. Plus, and then do it to the other one separately. Exactly, perfect. So my suggestion is do all the power rules across, right? So like, here there's a power rule, here there's a power rule, here there's, do those first. Once you've done that, then you're done with the power rule. So now you see, okay, let me see if I can use any of these two. Which one do you think you might use? And why? Now, you're adding two lines, right?
Yes.
So if you add two lines, see if you can figure out how to use this so that it turns into one.
Okay.
Yeah?
Right there, where the negative.
Like basically what you want, like negative one to show you. So this is a negative.
I mean, everything else is then I might be wrong.
Solutions are posted on the week 16 module page. You guys can check them out. A few more minutes, we're gonna have to move on though. So it's okay if you don't finish. It was just for you guys to practice. I wanted you guys to practice the condensing part. Okay, the rest was just extra.
I just got some here.
You got Did you get it?
No.
I'm guessing it's like negative one.
Yeah, so I got. I just got a lot.
You see, you got a two, right? Was there
That's
more
what
that you can pick up?
I wasn't sure if there could be one outside. Like, yeah. So that's why I'm.
Well, if you see something like that on website, and you accidentally didn't stake the two T and pick up the T, it's gonna be like one. Yeah. You know, as much as you can.
Oh, by like, yeah, yeah. I mean, only need. It's the number. But I didn't have to pay the two.
All right, guys, we're gonna move on. We're gonna move on. Okay, we're gonna finish. Just for additional practice. The solutions are on Canvas. Well, Siri. All right. Okay, guys, we're gonna continue on. If you're not done. So now what we're gonna do is we're going to apply some of these rules to see how we can solve exponential equations. We might not finish, so we'll continue next class. But that's fine. I don't want to rush solving exponential equations. This is hell of important. Who's taking calculus sum? Yeah, it's hell important for you guys too. You're gonna go lightning speed. You can do it though. All right, so let's see. Solving exponential equations. What we're gonna do next class, we probably won't finish this, so we'll start off with that, but what we're gonna do next class is actually do applications. A little bit of finance with exponential functions. And if you're doing the natural sciences, like biology, chemistry, we're gonna do some of that. And then to solve those questions, we're gonna need to do this. So that's the toolkit that we're learning. Yeah.
Just a quick question on 2A with the solutions. How do you know that it's broken up as log 6 instead of log 6x4?
Because the 6 is multiplying with the x to the 4th.
Okay.
So you're thinking of it as a product of two things. Everything that multiplies, split it apart.
Is this the 5.1?
This is all in 5.4. It's a big section, yeah. Yeah, this is still section 5.3. All right, guys, so I think up to now, we've solved all kinds of equations, right? Exponential, polynomial, rational, square root stuff. And so what's left is exponential and log equations. We're gonna focus on the exponential part. So we're gonna start with an example, and I'm gonna kind of break it down to explain a couple things that are gonna happen. So let's say you're asked to solve 4x, 4 to the x minus 5 equals 64. Let me give it a little bit of life. Otherwise, it's just so abstract. Last week, you learned that something of this form, you can write that as an exponential function, right? From base to some power of x. Maybe with a little transformation there to it. Okay? But pretend this is a function. The base is 4, so it's going to grow. And it's growing, and let's say you're doing a science experiment, and it's going to give you how much of something that you're producing at time x. So here, to solve this equation, we're basically, if I put that context to it, it's saying, at what time x will that thing that I'm studying produce 64 whatever bacteria or whatever it is that you're trying to figure out. Okay. And so that's kind of what that's what we need to know these skills, because that way I can answer that question. Okay. In terms of just an equation, remember, we're looking for the unknown number, so that when I raise 4 to that unknown number minus 5 produces 64. Okay. There's 2 ways to attack an exponential equation. One way is to not use logs, and the other way is to use them. Okay. So if I do not want to use logs, so we'll call this method 1, is you want these to have common basis. Let me show you what I mean by that. Common basis. So I want to see on the right, I have an expression, an exponential expression, but the base is 4. Can I write the thing on the other side as a power of that same base? 4. Can I write 64 as a power of 4? It's 4 to what power? The third power. So now I ask a question again. What number can I plug in here so that it equals this? 8. Well, what do you want this exponent to be so that it matches with this one? I want it to be 3. So I can think of just saying from here, I don't have to do any algebra. I just have to figure out, when does x minus 5 equal 3? Yeah. But you can see how the fact that I can write these as common bases, I basically then just say, when are the exponents equal to one another? Okay. And then yes, you guys are right. Just add 5 to both sides, and then it gives me 8. Well, this one is like the easier version, because there's not so much nasty algebra. Yeah. The second method is where you do have to use logs. And it turns out that you can use any log of any base. So we're just going to use the natural, because that one's useful for our calculator. Okay, so here we're going to use a natural log. So for this one, I don't want to think about common basis. I'm just going to leave this to 64. But if you guys look at your handout, let me write some more of the log properties here. If you look at your handout, there was these 3 rules. 1, 2, 3, and then there was the inverse properties. The ones that we did in the beginning of class. It was log base b of b to the x equals x, and b to the log base b of x. This is the one that, these are the two that we also did. And they're gonna show up again. This is the one where I was saying to cancel out the base of this exponential expression, you take the log of it, of that same base. So we're gonna use this onto this guy here. I have an exponential equation, I'm gonna apply logs to cancel off the exponential. So, don't write this part. Remember, like if I did something like this, it's gonna make up a number. What was the opposite of the fourth power? Fourth root. But it's not there, so you introduce the fourth root. You take both sides to the fourth root. So that these are inverses of each other and they cancel, right? Well, I want to cancel off this exponential expression. So I'm going to take the log, the natural log, sorry, of both sides. I'm going to take the natural log of both sides. Just the way we apply the fourth root, I'm going to take the natural log of both sides here. So I'm going to take the natural log of the left-hand side. And because I did that to the left, I have to do it to the right. So I take the natural log of this right-hand side. So we end up with ln of 4x minus 5 equals the ln of 64. Okay. Do you guys see how I have 4 raised to a power? So I have another rule that tells me what to do with inverse, with exponents. If I have something being raised to a different power, what happens to that power? I bring it in front. So think of this as like the m. And now because I introduced logs, I can use all these rules that you just learned. So we put this in front and use the power rule. So that I end up with x minus 5 times ln of 4 equals ln of 64. And then we stop here, okay? Put this on pause, okay? I'm going to give you another little analogy. Let's say you had this problem here. What would you do to solve for x and l? You would, you could distribute the 4, but you can also divide the 4 off, right? So you could divide the 4 off. So if I divided the 4 off here, what happens with these two 4s? They cancel out, and I end up with x minus 5 over 64 divided by 4, which is a number, right? Sure, I'm gonna leave it like that though. I'm gonna leave it like that on purpose, okay? I could do that because this is just a number and I'm just dividing it off, right? What's confusing about exponential equations where you then use logs is the notation's weird, okay? But you guys see ln of 4? Put that on your calculator. Someone do that for me. What's ln of 4? 1.83629? 386. It's just a number though. That's the point. This is just a number and this is just another number. So this is a number and this is a number. So the same algebra that you do here, we could also do here. So how would I cancel off the ln of 4?
64 divided by ln 4, is that would give us 16.
It will not. Maybe it will.
ln's gonna cancel out.
I think it gives you 3. Or does it give you 3? It gives you 3, right? It better give you 3. We'll see. We'll see why it gives us 3. Yeah. Okay. But algebraically, from here, this is where students get stumped. Because you want to distribute this ln of 4, and it just turns into a big S show. Okay. Just the way you could have also distributed the 4 here. It's just simpler if you divided it up, right? So when you get here, what do we want to do? Divide by ln of 4, not by 4. Here's another thing I see. Like that. You can't do that. That 4 is inside of the ln function, like sine and cosine and all that. Remember, we couldn't just cancel off what was inside like that. So we had to divide by the whole thing, by all ln of 4. Ln of 4. And just the way the 4's canceled, the ln of 4's will cancel. So I'm left with x minus 5 equals 3. 3 if you put it in the calculator. 64 over ln of 4, which, yes, you guys are right. It does equal 3. But what I don't want you to do is divide the 64 with the 4. That's what would be incorrect. It just stays ln of 64 over ln of 4. In this case, with the calculator, it's a beautiful 3. Okay? Question and a question. Yeah.
For another method, can you just make log of 4 and then cancel out the log of 4 with 4?
Correct. I'm gonna show you another one.
And then on the test, is there gonna be a section where we aren't allowed to use calculators, or are you gonna do it kind of like similar to the last one where you say make sure to show all your work?
I'll have to see when I finish making the, most likely not. Yeah. So yes, so in this case, you would leave this here, and if you put it in the calculator, it does give you a beautiful 3. But let's pretend you didn't put it in the calculator. From here, what would you do?
Add 5 to both sides.
Add 5 to both sides. So in this case, the answer is ln of 64
Over ln of
4
plus
plus 5,
that in the calculator and we'll spit out 8.
and you'll spit out 8. Yep. You'll spit out 8. But yes, this just equals an 8. There's a different way. I'm going to show you the other one. And that's what's tricky about these. There's like all these different methods. And they might require a little bit of different properties that you do.
Do you have to know all the methods because like in certain scenarios you can only use one or?
That's exactly right.
No.
All right, let me show you another one. Method 3. So here's where you want to use the inverse log property. That's the one Misha was talking about. So let's say you got 64. Because these two things are equal, when I took the natural log of them, they also were equal, right? But I can do, technically, I could have used the log of any base to do this. So because I have base 4 on the left-hand side, we could have also done log of that same base. So instead of taking the natural log, I could have done log base 4 to both sides. Like that. So it would have given me log base 4 of 4 to the x minus 5, log base 4 of 64. Why did I not do a different base? Why 4? Common base, right? And they would cancel. So then all of this, what's happening is kind of like this log base 4 and this base 4 cancel. So what's left on the left-hand side?
-5.
And then here I'm just left with log base 4, 64. Then you add the 5. And so then you get x equals log base 4 of 64 plus 5. How would you put this on the calculator though? Because it's log base 4.
Log base 10 of 64 over log base 10 of 4.
Or the ln as well, which is what we did here. So all three of these are 8. Can you guys see? Questions? Yeah.
But then also with this one, with all of these, you know, especially that one, and you can also make the 64, like, basically do what we're doing. for
Correct.
this one, but then with the logs, you know,
Correct, yeah. So no matter what, this can always be reduced to 8 somehow, right?
Yeah.
But now let's do one kind of what Khalil was saying, where this whole base, similar base thing might not work so nicely. This is not going to move forward. Let's do one where maybe some of those methods might not work. And then I'll have you guys help guide me here. Well, let's solve. So 7 to the negative 2x equal 8. Okay, let's see. You guys see here, if I try to do common basis, I cannot write the 8 as a power of 7. So that method won't work. So I can either do this method or this other method. You guys tell me which one. You want to use the inverse log one? Okay. The notes the notes do this one. So then maybe we'll do that one. Okay. So if I want to do the inverse log, what base do I use for that? I'm going to do log base 7. Log base 7. Log base 7. So I can do log base 7 of 7 to the negative 2x. Log base 7 of 8. And the left becomes log base 7 and the exponent there cancel. So then I just get minus 2x equals log base 7 of 8. So how do we get x by itself? By the negative 2. And then I'm going to end up with log base 7 of 8 divided by negative 2. Just on WebAssign, read the instruction carefully. Because if it asks you to round your answer, then you need a calculator to do that. Okay, yeah.
We don't do that, it's just back in the base.
On the test, I'm just gonna say leave it exact. All right, let's see, and this should be on the calculator though, if you wanted to check that. Negative 0.53, approximately that.
Wait, how would you check it in my calculator?
You would do the change of base that we learned last week. So then this would become ln of 8 divided by ln of 7.
All over. And then that answer divided by.
And then that answer divided by negative. If you solve this with this method, the natural log, this is the answer that you get. Okay. All right, let's see. I'm gonna leave these here. And I'm gonna give you guys, oh, okay, perfect. I want you guys to press solving these with your groups. Check with each other, please. All right, I got 1, 2, 3, 4, 5. Try these out. I'll go around and help you out. 2 to the x plus 4 equals 16. 2 to the x plus 4 equals. Oh, damn. All right. I got a little hard on there with you guys. Equals 16 to the x. 2 to the x plus 1 is equal to 3. And then I'm bringing in the e. e to the negative 4x equals 20. And then we'll finish it off with 11 e to the 2x plus 1 equals 20. Some of those you can use old method, some of them you can't, okay?
Let's use negative 4x.
Yep. Number two, guys, it'll be way easier if you use method 1, okay? If you try to use method 2 or 3, it's pretty narrow. Ignore it.
You just turn.
Yeah, but that's a wonder.
What's up, Alex?
Oh, okay. No, because it's still have an X. Okay, that's what you did. And this just means that we not just so because you're gonna collect really much. So three factors in this one that's
It's not wrong, it's just nastier. Because, like, let's say this problem had an X here. You won't be able to just divide the LM4 here. You would actually have to distribute it.
Did it with 3? I didn't see that now.
With number 3?
Yeah.
Yeah,
Oh, sorry, I mean method 3. But
If
maybe
you-
I did it.
if you did it with method 3. Yeah, okay, that's not that bad. So from here, like imagine you had imagine you had what you do?
Well, I need that some.
You would have to minus this guy over here.
Mhm.
So the algebra is just nasty.
Okay, I got it.
It's doable.
Mhm.
This is nasty.
Number one. Well, what would happen if you subtract? Zero. Zero. So, maybe having zero here. So I'm gonna tell you, remember you didn't want to. You didn't have a one, it's less than. So, you see that here? You see how here? See how here, we use the power, that's power, and we run around that. That's the whole table, that's the side. So for this one, we're gonna do the power, we do like for it's. And then you do that. Let's say you have this. It's not the same as.
I didn't do that.
It's negative one. So
I did.
Wait, no, it's not a law. You can't do that. Oh, yeah, you could do it. But I'm like, doesn't matter if the other said it's weird, all you gotta do it.
And it gets weird. And then stuff like-
Oh.
Yeah, but you have to get this.
Now we can use like that.
But how would you do it?
You guys know which question?
Two.
Well, but
Two.
It's to the power of 4. Yeah, to the power of 4 times x. So that's it.
Sorry, equals 4.
Oh, what?
Or is it 3? I know it's 3. What's 2? So you did minus 1.
Equals 2 to the power of 4.
2 to the power of 3.
4 power of 1.
And then
Yeah,
you
okay, so 2x plus 4 equals 2 to the power of 4x. Because x is open. And then you take the log, I mean, I guess, you heard the log, sorry. No, because the bases are equal, they're to represent the same. So you can take the exponents.
You make that basically 2.
Yeah, the bases are equal, just manage by the bases, because they're already equals.
Yeah, that's 4.
So you can just worry about the exponents.
So you did make it one.
Yeah, I did make it one for 2, I couldn't have to like.
Because there's an X in.
Yeah.
I don't know if you guys know what I'm saying.
Yeah.
Yeah. Well, when the bases are equal, you have to worry about the bases. Just get the exponent and just like do the work. Because the bases are complicated. You look at these,
Power.
or you could, if it's a computer game, that 12 work. Yeah.
Power.
Actually, it's part of-
The.
Yeah.
You find.
Right. The method. It's like. Yeah.
I think it's possible.
Or over three.
You gotta do the input back.
Right. Yeah, that's the X one, right?
Maybe it's not.
The log of the two and then
Oh,
X log of, yeah, so that's what they said, that master. Yeah, I'm just gonna check it.
Pick a number from 1 to 4.
Then you get it.
I think that's supposed to.
How long am I studying? Alright, so.
That's a lot.
Well, cause I have a 4 gap between this and my next one. 4 hour gap. Wait, sorry. Yeah. That's it.
Yep, let me just write the answers on these. All right, guys, let me just write the answers there in case you want to check. All right, so here,
You know what they're used to, guys, when I leave out, I was only gonna do this.
this one could be
Worry about number two.
x equals 0. This one should be x equals 4/3. This one should be x equals, you can either write it as log base 2 of 3 minus 1, or you can write it as ln of 3 over ln of 2 minus 1.
No problem.
If you approximate it, it's negative 0.58. No negative. That one's bigger than that one. And then for 4, it's x equals ln of 20 over negative 4. And then this bad boy is ln of 20/11
Yeah.
minus 1 over 2.
Let's go. All right. That's what, no, we never do that. That was, yeah.
Did you have a question, Amber?
I got a bigger problem. So true. Is this? Yeah.
All right, guys, let me do number 2 with different ways, okay? It should be positive. The negative should cancel. Let's see what's up. Okay, what method are you guys using?
Number one, dude.
Yeah, if you use method 1, it would be 2 to the x plus 4, and then the 16, you would write it as,
Two, the power of 4, and then X.
and then x, right?
And multiply.
And then because of exponent properties, these end up being multiplied. Yeah,
And then you can do a log.
now you want, for this to be equal, the exponents have to be equal. So then we get x plus 4 equals 4x. And then
Minus the X.
And then you want to combine all the x's together, so you minus the x, good. So then you get 4 equals
4X minus X.
x, which is 3x, and then divide by 3. So there's where that 4/3 comes, okay? That's what that was my hint. Yeah, but if you didn't want to do it, you're like, hell no, okay, I want to do it right away. Let's say you wanted to do method two. Questions on method 1? Okay. So if I do it this way, which other method were you guys doing? You're doing method 3? You do method 3. I don't think I'll have time for all of it. So if you do method 3, what do you guys do? Log of what?
Log base 2.
The log base 2? the log base 2 of 2x plus 4. Log base 2 is 16x. So then, I'm guessing you guys canceled these, right? You got x plus 4. And then here, what did you guys do?
I would.
You moved the x? You can't leave it because you can't have your x equal something with an x on it. Otherwise, it's not done.
Yeah.
So you have to bring it down. Because 16 is a power of 2, you can simplify that. If it was not, like, if this was a 17, the problem gets even nastier, okay? I don't think I'll have time for that. But because 16 is a power of 2, remember the log is supposed to equal an exponent, right? 2 to what power equals 16? 4. That means this right here is just 4. So then this becomes x times 4, which is 4x. And then you're back here. Well, then you get the same answer. Okay? All right, guys, I'll stop there.
I feel like sometimes we tell you when class.
Oh, 100%. We used to have an 18-week calendar, and then the district was like the semester was 18 weeks long. And then the district said, no, we're shoving everything to 16 weeks. We're just gonna add like 10 more minutes to your class. I'm like, sweet, the time that students start to pack up. Yeah. All right, guys, you have a question?